One would hardly do Newton's method by hand in this day and age, but just to help get a handle on it, let's look at an example. Let's find the positive root of f of x equals x squared minus 2. And again, we know what the answer to this question is. It's the square root of 2. But our purpose here is just to see Newton's method in action. Let's take a look at this thing. The thing about Newton's method, remember, is that we need a starting guess kind of near the root for Newton's method to work. The root is, if here's 1 and here's 2, this root looks like it's pretty close to 1.5. Let's use that as our starting guess. X sub 0 equals 1.5. And now it's very plug and play. We'll need the derivative of this, which is a 2x. X sub 1 equals f of x sub 0. Nope, sorry. Equals x sub 0 minus f of x sub 0 divided by f prime of x sub 0. So 1.5 minus, we stick x sub 0 into f of x, 1.5 squared minus 2. We stick x sub 0 into the derivative. And we plug this into our calculator. I'll do that off screen. And we get x sub 1. And the hope is that x sub 1 will be closer to the root than x sub 0 was. And now to get closer still to the root, we need x sub 2, which is x sub 1 minus f of x sub 1. So x sub 1 squared minus 2 divided by the derivative of x sub 1, so 2 times x sub 1, and we stick this into our calculator. calculator. Again, I did this off screen. 1.41427. And now we can repeat this until we're sick of it, or more to the point, until our answer is as accurate as we want it to be. I mean, I know I said find the positive root, but we're never going to get there exactly. The best we are going to do is approximate. So what's our terminating condition? How do we know when to stop? Well, first we decide how many decimal places we want. You'll notice we've been keeping 7 decimal places. The indication that it's time for us to stop will be that our x sub i's stop changing. And that happens here. When we calculate x sub 4, we get x sub 3 again. And x sub 4 and x sub 3 aren't really the same numbers, but any difference between them is occurring out here in the 8th or more decimal place. As a matter of fact, this is correct. To 9 decimal places if we'd kept that many. So at least when it works well, Newton's method is extremely fast to get our approximation. We had to calculate x0, x1, x2, x3, x4 to get 9 decimal places of accuracy. And a computer could do this pretty much instantly. So when Newton's method works correctly, it's a very powerful algorithm. It does sometimes fail to work correctly. Newton's method has division in it. So anything that gives us division by 0 or division by something very close to 0 is going to be a problem. Things can go wrong it's not really within the purview of this class to give a detailed analysis of Newton's method, but let's go ahead and see one example where it fails, and we'll do that in its own separate video.